I open.
All right. Our final speaker is Miguel García Fernández, who is going to talk to us about Groenewold-Moyal twists, integrable spin chains, and THEORY.
Okay, thanks for the introduction and thanks for giving me the opportunity to speak here. So I want to present a very recent paper I did in collaboration with my supervisor, Ricardo Posada. So before starting, let me sort of motivation of this point. So the motivation is elicit integrability. So as you know, there are many possible ways to realize this duality, and the most well-known is just the duality between n equals 4 super-Yang and ADS5 cosec 5. And then there is also a well-known fact that when looking at the spectral problem at the planar limit, there is integrability emerging. So in the case theory side, there is an integrable spin chain, and on the on the string theory side, there is an integral sigma model. And in fact, these two are sort of the same realization of the same integral model that is invariant under this SU2/2 square sigma. Okay. Now, what we want to do is to try to deform. It's not correct. Try to deform this setup. In particular, we want to consider some deformed gauge theory and some deformed string background. And the reason, one motivation to do this is because we want to study gauge theories that are sort of more realistic or more complicated just by breaking some of the symmetries, for example, conformal symmetry or supersymmetry. And we want to do this not in a generic case, but we want to study deformations that somehow preserve integrability. So somehow we should recover some deformed version of our spin chain and some deformed version of the sigma model that hopefully we will correspond to the same deformation of the looking. Now, there's been a lot of work in understanding the formation of sigma models, but less is known about the formations of these theories. So in my talk, I want to consider the formation of the spin chain with the goal in mind that this deformation of the spin chain should give some information of the deformed gauge theory that is behind it. Okay. Now, there are many possible ways that we can deform this spin chain. For example, one can consider elliptic deformations or quantum deformations, but here I will consider another type of deformation that goes under the name of Drinfeld twist. And there are two reasons to study this Drinfeld twist. The first one is because Drinfeld twists provide a very clear way of how to deform these spin chains. And the second one, maybe more interesting, is that this Drinfeld twist has a very nice holographic interpretation because the same machinery that is used to deform the spin chains can be used to deform the gauge theories by doing what's called Stark deform. And these Stark deform gauge theories were conjectured to be holographic to homogeneous Yang-Baxter deformations. So because of this conjecture, in fact, it makes sense to study Drinfeld twist deformations of spin chains because somehow there should be the spin chain underlying this constant. Okay. So there have been very recent work on Drinfeld twist deformations of n equals 4 super-Yang spin chain, in particular by performing what's called dipole deformations and Groenewold twists. But here I want to consider another type of deformation that is called Groenewold-Moyal twist, which is probably the most well-known way of introducing not commutativity in gauge theories. And as I will try to explain, to do this deformation, we need that our spin chain to be invariant under a symmetry algebra of rank greater than 1. So that's the reason what I consider here the possible minimal setup, which is just two independent invariant spin chains. Now here there's some technicality, but this spin chain is not a spin chain of n equals 4 super-Yang, and the reason is that there is no SL2 times SL2 subsector on n equals 4. However, this spin chain is still interesting for holography because it can be viewed as a spin chain that appears in this ADS3 times S3 times 4 spin chain. Okay. So roughly speaking, this will be the part of my talk. First, I will try to explain this SL2 times SL2 spin chain, which I denote here by XXX minus 1/2 square. Then I will try to introduce what the Drinfeld twist is. And in particular, I will focus on the Moyal twist. And finally, I will try to deform this x minus 1/2 square by this Moyal twist. Okay. So as I said, this spin chain is invariant under two copies of SL2 that I will denote by left and right. And these generators transform into the so-called spin minus 1/2 representation. So this is an infinite dimensional representation that can be expanded by introducing two sets of bosonic oscillators, A for the left copy and A bar for the right copy. And essentially with these oscillators, we see that T cartan is essentially the bosonic oscillator number, J plus is just the creation operator, and J minus is the annihilation operator. And then the Hilbert space of our spin chain is just the lowest weight module of this representation. In particular, it is spanned by all states with fixed number of excitations, and this can be just represented by acting with the bosonic creation operator on this ket 0, which is just the lowest weight state of the algebra. Okay. Then what's the Hamiltonian of this spin chain? So the Hamiltonian is of nearest neighbor type. So that means just it's a sum over Hamiltonian densities that acts only on two sides, and it has periodic boundary conditions. And because it's independent on the two SL2 copies, this is just mean that the Hamiltonian is the sum of one XXX acting only non-trivially on the left copy, and the same Hamiltonian acting only non-trivially in the right copy. Yeah. Then the Hamiltonian density is very well known. It's just this harmonic action. So essentially, it has some diagonal term proportional to the harmonic numbers and some off-diagonal terms that redistributes the excitations in all possible ways in the two sides. And because the Hamiltonian density only redistributes excitations, there is particle number conservation for both types of species left and right. And this is just a consequence of that our model is invariant, particularly under the character of this system. Now, it happens that this model is integrable. So it's of rational type based on Jangen symmetry. So a possible way to deform this spin chain is just by looking at deformation of the matrix in such a way that these deformations preserve the Jan-Baxter equation. And this is preserved with what Greenfield's twist do. So in this Greenfield twist setup, when you start with some coproduct and a matrix that defines your spin chain, the coproduct is just this delta X. And what we do is just go to a new coproduct, a newer matrix, just by doing this transformation, where now the deformation data is inside F, which is called this Greenfield twist that acts on two sides. And then the basic claim of Greenfield twist is that if your initial matrix solves the Baxter equation, the twisted one will also satisfy the Baxter equation, provided the twist satisfies this three-body relation, which is called the Greenfield equation of the cosine condition. So this can be simply abstract. So I want to consider some particular case, which is the Moyal twist. So as I say, in this setup, you have two SL2 symmetries. So in particular, we define the Moyal twist as this operator, the exponential of J minus left, wedge J minus right, where here Chi just called the parameter deformation. So this F is in fact a one-parameter family of deformations that are continually connected to the identity in the sense that if Chi goes to 0, we just recover the one operator and we recover the deform. Okay. Now, this twist is also abelian, and this means that it's based on two generators that commute, in this case, J minus left and J minus right. But it's non-trivial because it's not diagonal. And by this, I mean that states with a fixed number of excitations are not eigenstates of the twist. In fact, the action of the twist on some state with a fixed number of excitations produce these tails with less and less excitations until one of the two, either left or right, reaches it. Okay, so it's non-trivial. Now, what can we do is the following. So we can take the matrix of our spin chain, deformed by this Moyal twist, and compute this deformed Hamiltonian. The deformed Hamiltonian is the following. So it's still of nearest neighbors type. That means that Greenfield twist preserves the range of interaction. It's still periodic boundaries. And the Hamiltonian density is deformed in this way, just via similarity transformation with F. Okay. Now, originally we have a spin chain with left and right copy independently, but here, because the F twist contains left and right operators, now there is mixing between both types of excitations. Now, the next question we can ask is what are the symmetries of this model? So because we're introducing this twist, we expect that some of the symmetries, some of the original symmetries are broken. And indeed, this is the case. So in particular, because the twist annihilate excitations, particle number is not considered anymore. However, and this will be very important later, symmetry under the negative root generators, this J minus, this is will preserved in the deformed state. So what we have done so far, so far we have constructed a new Hamiltonian that is not Hermitian, and this is very clear because now the Hamiltonian contains these J minus operators. It does not have excitation number conservation. So the next question we can ask is how to compute the spectrum of this model. And even, is it diagonalizable? So a priori it's not guaranteed because the Hamiltonian is not Hermitian anymore. So now, following the standard root algebraic answer, instead of diagonalizing the Hamiltonian, we diagonalize the transfer matrix. So we introduce a twist monodromy, which is just a product of twisted matrices, and then consider the trace over this A, which is the auxiliary space. So if you do this trace over the auxiliary space, we get the so-called transfer matrix, which is this object here. So it's just a product of some deformation of the left copy and some deformation of the right copy. And we see that the parameter deformation goes to 0. We just recover the twisted undeformed transfer matrix for the left copy times the undeformed transfer matrix for the right copy. And this just means that originally in our original model, left and right excitations are completely coupled, right? But now, because of the twist, there is coupling between left and right excitations. And in fact, now the corrections are proportional to these S minus operators. And these minus operators are just the J minus, the negative generators acting on the full speed chain. Okay. So now what we do is try to diagonalize this twisted transfer matrix. So the first thing we notice is the following. And so we know that all states of the undeformed theory that are lowest Moyal states, and by this I mean that are annihilated by S minus, are automatically also in states of this twisted transfer matrix. This is just very clear because of the form of the transfer matrix. So all we need to do is just to see how the descendants are deformed. Okay. So to compute the deformation of the descendants, we do the following. So we know now that the particle number is not a symmetry of our model, so we cannot diagonalize this twisted transfer matrix by states with a fixed number of excitations. But because the twist only annihilates excitations and does not create them, we can still try to diagonalize in a subspace of our Hilbert space with a fixed maximum number of excitations. So instead of considering a state with a fixed number of excitations, we consider some linear superposition of states ranging from some state with fixed maximum numbers of excitations to another state where one of the left, right particle numbers. So now what we can do is just try to solve the eigenvalue equation for these new answers. So if we do the eigenvalue equation, we see that because the twist annihilates excitations, we get different components, and each component will have a different particle number. Okay, and because states with different particle number are orthogonal, you can always project into each of these components. And in particular, if we look at the component with maximum number of excitations, we just recover the undeformed eigenvalue equation. Okay, and this means two things. The first thing is that in this generic superposition, the component with the maximum number of excitations is just an eigenstate of the undeformed theory. So this makes sense because this means that there is a one-to-one correspondence between eigenstates of the undeformed theory and eigenstates of the deformed theory. And secondly, and most important, is that the eigenvalues are not deformed. And the eigenvalues are just the eigenvalue associated to this undeformed eigenstate. Okay. So now the algorithm is very clear. So you start with the undeformed data, and this data is just some undeformed eigenstate and some undeformed eigenvalue, and we just compute the corrections of this undeformed eigenstate by solving recursively the eigenvalue. Okay. Now it happens that from some initial undeformed eigenvectors, there is no solution to the eigenvalue equation. And this means that this undeformation state should be associated in the twisted model to a generalized state. And this is very natural because we are working in a subspace, finite subspace, and in this finite subspace, J minus is essentially a triangular matrix. So essentially, it makes sense that the restriction of the twisted transfer matrix is subspace to be non-diagonalized. Okay. Now, a possible way to get right of this generalized space is doing the following. So as I told you, there is some residual symmetry, and this is just S minus, the negative root generator. So instead of trying to diagonalize this transfer matrix in an eigenbasis of the Cartan, we can try to diagonalize in an eigenbasis of this S minus L and S minus 1. So now eigenstates will be labeled by these two complex value numbers, M left and M right, which are just the eigenvalues of the negative root generators. And if we do this in this eigenbasis, something interesting happens, and is that all the coupling between left and right copy is just through a constant, to this M constant. So what I can do is just to define a new effective parameter deformation, where the information of the other copy is hidden to these two new deformation parameters. And by doing this procedure, we see that our original coupling model between left and right essentially did decouple into two independent deformed XXX spin chains, one for the left copy and the other one for the right copy. Okay. So now we can try to find factorized solutions for both twisted, for left copy and right copy, and essentially we are the same. Solid one is. And now we see something interesting, is that this new twisted model is just coincide with the twist XXX minus 1/2 spin chain that appears in the dipole deformation of n equals 4 separated. So this dipole deformation is just a deformation that is made of one of the air symmetries of n equals 4 and some light on momenta. And because the air charge is triggered on the SL2 short sector, essentially the twist in this subsector reduced to this operator, this factorized operator. Now it happens that this twisted model can be solved via some more advanced integrability techniques for TQ relations. So essentially what we can do is just borrow these TQ relations and apply this to our problem. So if we do this, we can, in particular, we can compute the spectrum of our Hamiltonian, of our twisted transfer matrix. And something surprising happens is that now the energy is non-trivially deformed. So now here I'm putting the correction to the vacuum. So now we see that the vacuum is non-trivially deformed. It is parameter deformation in even powers, and with a leading term that is therefore 1 over G cubed. And in particular, we see two things. The first one is that if J increase, J is just the length of our spin chain. So with the length of the spin chain increase, the corrections decrease. And in particular, in the J to infinity limit, they go to 0. And this is also very natural because in this limit, essentially our excitations do not interact. So we have a free model in this infinite length limit. And the second thing is that the corrections depend on this product of M left and right. And this is something non-trivial because if one of the two are 0, essentially the correction vanishes. But the twisted transfer matrix is still non-zero. So for example, so let me go back. If M right goes to 0, then C left goes to 0. So the left copy is undeformed, but the right copy is still deformed. Okay. So the only way to recover an undeformed model is just making the two M left and M right. So essentially, let me summarize what we have done. So we have constructed some Moyal deformation of two SLT invariant spin chains. We have seen that the Hamiltonian is not diagonalizable in the and with undeformed eigenvalues in the Cartan eigenbasis. And we have also seen that in the eigenbasis of the negative root generators, the energies are non-trivially deformed. So there are several open questions to this problem. So the first one is trying to understand integrability methods for these non-diagonalizable models. So as far as I know, there is no clear way to reproduce generalization vectors using integrability. Now, the second open question is how to compute these TQ relations of the different model from first principles, and from first principles, I mean from the separation of variables framework. Then another natural generalization should be to construct deformation of the full spin chain. So whereas a spin chain is just a particular subsector of the ADS3 spin chain, so it would be also interesting to construct deformation of the full ADS3 spin chain. Also, another natural generalization is to construct deformations at higher groups. So this Hamiltonian, which is nearest neighbor, it just corresponds to the first order first loop expansion. And each time you increase the order, you are increasing the rate of interaction. So in some sense, it should be possible to introduce these Greenfield-twist deformations for long-range spin chains. And the last one, maybe also very interesting from the point of view of theory, is try to understand the meaning of this twisted spin chain from Miguel's theoretical point of view. So essentially, because of this twist, conformal symmetry is broken, and in particular, dilatation operators no more asymmetry of our model. So, in fact, it makes sense to see now this twist Hamiltonian, which operator corresponds in the underlying differentiation. And with this, I finish on thank you.
Well, thank you for the talk. And for questions.
So if you consider string theory,
Say that
if there is an
yes.
So if you consider string theory like S3 as 3, then it would correspond to this information of ADS3 space model.
Yeah, I'm not an expert in these, but yeah, somehow this was what just going with the master information test.
Well, it's here, right?
Yes.
One is contracts because it's different information. So you have one parameter, so
Yeah.
also have a torus, and it's 3. And the question is whether you take this torus, well, one circle from ADS3 and another one from S3, or both circles from
Yeah, I don't know this.
ADS3.
All right. Any more?
Thank you for the talk. So, can you repeat why you were going to ADS3 and not doing ADS5? And if you were doing an ADS5, would you expect any structural difference?
This is impossible to do in ADS5 because we are considered here. So our spin chain model is just invariant under 2 copies of SL2, right? And in n equals 4 superior means there is no closed subsector with this symmetry even at 1. So that's the
Would
reason.
you be taking the full issue?
Yeah, you can include it.
Would you expect anything structurally different?
No, a priori the structure is the same. Because yeah, the structure is the same even in all cases that you have this twist with these negative group generators, the structure is always the same. If you work in the eigenbasis of the cartan, you have non-diagonalizability, and in the eigenbasis of the man, you have Schwarzschild. So yeah, the structure should be this.
All right. No further questions? Okay. Let's thank our speaker again.